Good evening, students. We will start in 5 minutes. Good evening to all. So we can start. Shreya, please start with introduction.
Yes. Good afternoon, all. I am Shreya from BAJA Alumni Committee. So, welcome to this second session. So, this is the Ansys training session designed exclusively for BAJA IC India teams today. So, in this second, we will cover basic structural analysis and result interpretation, parametric optimization and its application, basics of CFD and result interpretation. So we have Mr. Mayank Vivedi with us for this session. He is an experienced engineer specializing in automotive crash domain and the intersection of simulation and machine learning. He will guide us through basic structural analysis and results interpretation and parametric optimization. Also, we have Mr. Rohit Sangwan with us. He is a tech lead in ANSYS CFD. We will discuss the basics of CFD and result interpretation. He is an expert in thermal analysis, critical for optimization, aerodynamics, and cooling systems for your BAHA vehicle. So, at the end of the session, I request the participant to put their queries in the chat box. So, that's all from my side. Over to you, sir.
Thank you, Shreya. So, good evening, everyone. This is Mayank, and I've been associated with Baha from my college days. Like, I have started participating as a student, and then so far I have been with multiple roles. So I've started with as a student, and then I also mentor some teams, and then after joining Ansys, I was coming here as a judge. So this was brief collaboration with Sehi Baha. And today's session, what I observed is students they study things, but they do not correlate those things with what they show. So the results part which they showcase, sometimes they do not understand from where those values or those fringes they usually comes, and what basically they should interpret out of it. Okay, so that's the reason I wanted to talk about all these aspects of um, like analysis, be it structural analysis, be it fluid analysis. So this was the brief context by what I have started, and I put together the agenda slide. So in today's session, I mean, earlier also I had done multiple presentations, but those times I kind of have used lot of text or lot of theoretical concepts which I wanted to explain. But this time I put less content, and I kind of have I will use some demos to give you brief understanding, and maybe we will also discuss about the results part. So let me, with this note, I will start. I will share my presentation. Anyone can confirm whether my screens are visible.
Yes, sir.
Yes, sir. It is visible.
So you can see the presenter mode or the screen mode. I mean, the slides deck is Aditya. Do I need to swap the slide mode?
Yes,
Hello.
sir.
Okay.
Yes.
Okay, no problem. Maybe I should showcase the presentation PowerPoint live. Okay, and says basic training. Where is it? Okay. Okay. It's not shown. Okay, so let me. Okay, let me share my screen again. Please confirm when you can see it. So this is okay now?
Yes, sir.
Yes,
Yes.
yes.
Okay, okay. So yeah, hi everyone. Again, so we can start. The content of my presentation would be we'll briefly discuss about the analysis type. So I will try to classify the analysis based on what understandings which we have, maybe with respect to time domain or with respect to loading type. Okay, and then with a conclusion of that part, I'll also talk about the demo. I'll showcase one case study, and maybe we'll also discuss about the result interpretation part, and maybe we'll also talk about the references where we can gather or we can understand more on analysis point of view. Yeah. So with that note, I will start. So when you say analysis, structural analysis can be segregated or classified based on multiple factors. So these are the typical factors which impact it. So let's say if I talk about load type, so there are multiple loads. Uh, so based on that load type, we have analysis classification. Then we have time dependence, whether the your load or the analysis is time dependent or not. Then maybe rate of loading or impact. So that way also it can be categorized, and then also based on material behavior. So this from the past few years, I'm seeing that students are not paying much attention on the material behavior type. So maybe that we will discuss in detail. Then maybe we can also talk about the geometric behavior. Okay, and then we can also talk about nature of response. So um, So first type of classification is the load type, where we have two types of load. One is a static load, another one is dynamic load. So when I say static load, it is basically the dead loads or pressure loads which are acting on a body. Okay. So and they are more or less constant, or they can be slowly varying in nature, where we can also call it as a quasi-static load. Yeah. So these are static loads. Then we have dynamic loads. So dynamic loads are either the magnitude is varying, or the direction is varying, or both magnitude and direction of the load is varying. So these, what kind of loadings it will impact, those also we can look in brief glance. Yeah. So we have here periodic loads, where which can be an harmonic signal or sinusoidal loading, which is basically implemented on rotary machineries, which are generated because of those rotations. Then we have random loads, where your road profiles comes into picture, or maybe the turbulence because of air or some other external disturbances which are coming on to the machines. Then we have transient loads, like sudden applied loads, either some steps or some pulse or some ramping. So those kind of segregations we can do for transient loads. Then we have impact load, which are high speed collisions. So drop, crash, blast, those are kind of very high impact, very rapid or high kind of impact loads. So if you see on the right hand side, we have, I'm just demonstrating a static load where your load is kind of constant. So this comes where a component is there and it is basically standing or lying with its own weight. So this weight also known as dead load. Yeah. So which is basically a constant value with respect to magnitude as well as the time. Then you have dynamic loads, which is again periodic, or it can be random, or it can be impacts, those kind of things. So in impact we have, so you see the difference between impact and gradual load. So impact load is somewhat where your impact time is very small. So here, if you see, the gradual load is something which is applying very quasi-statically. So this is taking huge time to, basically to be applied onto the body. Or if you see the equilibrium disturbance would be very small at each time step. So that's the reason they are gradual load, and they can be, there is no effect of inertia in these cases. Whereas if you see talk about impact loads, you will have inertial effects also. Then you have fatigue load, where your times, your load magnitude is varying, or it can be, it can be, I mean, completely reverse also. So those we will also look at in brief in upcoming slides. So when I talk about time dependence, so here you have static analysis, which where time component is not there. So basically, when I say time component is not there, that means it will go. There is no effect of inertia and dampings in these kind of analysis. Whereas if you have quasi-static analysis, where you have slowly varying loads, like we talked about, where still inertial effects are negligible. So these kind of analysis you can see when you have bolt tightenings in a model. So we prescribe pre-stressing to give the tightening to the bolt, no? So that way we can do those things in quasi-static way. Then we have dynamic analysis, which is purely a time-dependent analysis where let's say you have free vibrations in the system, you have forced vibration in the system, you have multiple responses, harmonic response, modal analysis, transient dynamic analysis. So those are dynamic analysis which has quite dependency on time. Then we have impact, shock, and crash analysis, which is very short duration event with high magnitude of loading. So for those kind of simulations, we require explicit dynamics because it is mostly uh, time step driven where the convergence would not be of a challenge here. Maybe this is quite detailed and understanding to why those impact loads are solved from explicit analysis. That maybe I can give you certain references which you can, as an homework, you can go through it and you can get those understanding. Maybe you can connect me after this also if you have any query in terms of the references and understanding. So then moving on to rate of loading. So we have static loads which are very slow. So rate is very slow. And can we solve with implicit? You have quasi-static, which is also which is not very slow, but it is slow. We assume that the inertial effects are very negligible here. So this also can be solved in implicit. Then you have dynamic loads, where you have moderate rate of loading. So it can be solved with implicit as well as explicit. Then comes shock and impact, which is where rate is fast and you have to solve it with explicit because these two are very, or I would say highly nonlinear kind of problems. So when you have nonlinearity into the system, since with respect to nonlinearity, since these are nonlinear, if nonlinearity are there, you will face convergence challenges if you solve it with implicit. So convergence is the thing which is of challenge here. So we solve those things with explicit, and even other advantages are also there with respect to explicit. Why we solve it? So those maybe would be quite in depth, and with the interest of time, I have not included those concepts also here. So maybe those can be maybe you can note it down and you can go through it as an homework. Now comes the classification based on structural behavior. So when I say analysis, linear analysis or non-linear analysis, so all if you see you have a you have an assumption when you drive those strength of material equations, like your deformations would be very small. Yeah. So, and even the Hooke's law also state like your response would be linear within elastic limits. So, when you have linear analysis, the behavior of your material would be this red line, which is kind of ideal because once it reaches your yield modulus or yield limit, it will kind of goes into plastic zone where your slipping will happen and the behavior would no longer be linear, right? So the linear analysis would not would be till your yield limits. So if you see, let's say your yield limit, maybe you have given either 350 or 50 megapascal, and in your material you are getting, or sorry, not in your material, in your structure you are getting a stress value, or your von Mises stress is reaching somewhere around 600 or 500 or maybe more than 450. That means your material is going into plastic zone. So what you need to do is you need to first activate the large deformation mode, large deformation option from mechanical. If you are doing static analysis and if you are doing dynamic analysis, you need to basically change your, I mean, first step is to change your material to elastoplastic material because initially if you are using only till this limit, then you have only elastic material. When you define the plastics limit also, that way your material would be your elastic as well as plastic. So elastoplastic response it will generate. So those kind of materials you have to include if your stresses, von Mises stresses are way beyond the yield limit. Yeah. So that way, if you classify based on material response, so this is how you have to define. Now, when you goes into non-linear zone, non-linearity itself is of multiple types. One is geometric non-linearity, where you see large deformations are coming into the structure. So that way you have non-linear. Basically, your non-linearity has included into the system. Okay, so one such example of this large nonlinearity example is you have, fishing rod, right? So that rod is somewhat, it can go like this also. So those kind of, if you see in this fibers, you will have nonlinearity into the system. Then you have second non-linearity type. This is first type. Second type is your material non-linearity. So when you have material non-linearity, that means your material has either plasticity involved or viscoelasticity involved or hyperelasticity involved, or maybe creep based on time. It is losing its grip. So I mean, since this is a very time-taking phenomena, so let's not talk about this. But yeah, plasticity, viscoelasticity, and hyperelasticity. Like somewhere you have your your PPP plastic kind of materials. So that's where you need to define viscoelasticity, or if you have rubbers, hyperelasticity, viscoelasticity, all those things will come into the picture there. And if you have, if you are, if you are if you are if you are controlling your material response, because there is one material which is very generic, which is elastoplastic material. Okay, so if you are controlling the, I mean, maximum responses of material can be captured with this material model alone, which is elastoplastic material, which has, I mean, where you can maybe you can approximate your elastic behavior, and you give multi-elastic or bilinear plasticity. So that way, most of the responses it can capture with this elastoplastic model. So generally, this is what the model which we generally use in the analysis wherever we use. So even if you talk about your dynamic analysis, maybe you do it in Dyna, no? So in Dyna also we have this material model called MAT24, which is MAT piecewise linear plasticity. So that will have elastic as well as plastic response, because you will define your sigma y, and then you will give a true stress versus strain curve, which defines the plasticity values. Then you have contact nonlinearity. So wherever you see you have contacts in the system, like maybe you may not be defining the contacts for your analysis. Like let's say you have, I'm just drawing a side view of a structure, maybe your roll cage. So you have these, I mean, you have these members which are welded together, right? So as of now, for assumption, I'm not sure how you are following it. Maybe you might have done some 1D analysis here, and then based on that 1D, you have assumed it as a continuous member, right? So when you are assuming it as a continuous member, you are kind of neglecting the stiffness which is coming because of these contacts. Like when you are welding it, so either you may be, some of the reason because of heat affected zones, your strength would be decreasing, and somewhere because of you're adding more material, somewhere your parent material strength might be increasing. So here you see, in a nutshell, these will have variable stiffness based on the joining method uh, uh, application. But what you are assuming it as a, since you are kind of doing a 1D analysis or 2D analysis, you extrude the complete roll cage as a single frame. So which is basically approximating your analysis. So those results would not be of use. So please try to understand those concepts and try to use more detailed understanding how better we can understand or model our roll cage or the frame or the like joints or contacts which we have included. So in these locations, you either can use maybe tied kind of bonded kind of contacts. So though that way you can also control the stiffness of these joints, right? So this all about structural behavior. Then maybe um, uh, other parts are not very relevant. So I have jumped into the just to explain the concept of dynamic loading. So let's say when we have a dynamic loaded part, right? So my loading is basically changing. So that means either my magnitude of the load can vary or the time of the load can vary. So based on that, if you see here, um, I have two concepts. One is we have sigma mean and we have sigma v, which is the variable stress, or this is your mean stress. So you have sigma max and sigma min. So sigma max is somewhere, let's say for repeated stress. Repeated stress is somewhere it will start from zero or somewhere on top, and then you will have somewhat sigma max, and then it will come down. And same way you will have alternate stress, which will start from your sigma mean would be negative. It will start from negative, and then it will go into positive zone, and then again it is come back to negative. Like so it is more of a compression and then tension, and that way multi kind of loading will happen. And same way for fluctuating, you have sigma mean, it will start, and then sigma max, sigma. So this part would be your sigma v variable, and this is the reverse stress. So your mean would be zero. When your mean would be zero, you will have sigma max and then sigma min, and then your loading would get implemented. So now why I'm explaining this concept is, let's say you have a sigma mean. If you talk about sigma mean, everywhere you see, like when you have a static load, your sigma max and sigma min would be a single value. So when I put that here is like, let's say sigma max is sigma plus sigma by 2. So you will get only sigma application as a sigma mean. Okay. And then when you talk about your sigma variable would be a 0, right? So when this V will not be there in the system, your system will always be uh, towards static loading, right? When you have sigma V in the system, like your variable stress is in the system, that's where you see the failures would happen below your yield limit. So when you have sigma, like if you recall your SOM equations, you have defined or you have derived those equations assuming that your loading is not changing. So if you have sigma applicable, your loading will not change. When your loading will not change, that means you will not have fluctuations in your model. So that means those driven formulas would be applicable when you have sigma v will not be there in the system, right? So when you have sigma v, like your variable stresses, that means your material would fail because this is cyclic loading, right? It will, like your component will go compression, and then it is again sorry, it is in tension, and then it is in compression. So your component can fail before the yield limit also, right? So that's the reason uh, the fluctuation or the fatigue computation is very much needed when you are designing for a cyclic loading. So if you see in your frames or in your maybe in your vehicle, you have tie rods, you have A arms, those mountings, brackets, those would be subjected to fatigue loading. Because now when we say all the endurance limits, you see those Soderberg-Goodman equations, they are driven for sigma mean, right? Why that sigma mean is there? So if you see here, uh, you have sigma mean as 0 for reverse stress. So when I say sigma mean 0 here, that means your sigma mean, you have sigma max and sigma min by 2. So that means 2 times of sigma by 2. You will have sigma as your sigma loading. But if you talk about sigma v, So here is when you say sigma b, so you will have sigma max and then minus of minus sigma. I mean sigma minus of minus sigma. So that would become 2 sigma, and 2 sigma by 2 would be your sigma. That means the kind of when you have reverse loading, reverse stress loading or cyclic loading, you will have loading which is exactly opposite to your static loading. Like in a static, you will have sigma min as sigma, whereas in uh, completely reverse loading, you will have sigma b as sigma. I mean, the variable part would be sigma and your mean part would become zero. So when this is the situation, that's where you see all your limits, and this would be your worst case scenario. I mean, if you are designing for this completely reverse loading, all these loadings would be your and would be okay criteria. So when you that's where you see all those limits and all are derived across your sigma v's, like when to cater your so when you have sigma mean as zero. So that's where you see those midline would be your sigma m as zero, and then you will have these kind of curves for your Soderberg, Goodman, and Gerber. So this was briefly about dynamic loading. I understand this is too difficult to understand, but yes, if you think about these concepts, like completely reverse loading are worst scenarios, and why, I mean, we cannot apply those sigma is equals to f like your stress and strain relations, you cannot use those equations here directly. That's the reason, because you have not derived those equations for your kind of these fluctuating loadings. Then just briefly touch upon what kind of loadings, I mean, fatigue analysis you can do. So you have low cycle fatigue, which is high strain where plastic deformations are high. Okay. And these are like components which is where you follow strain life concepts. And when you have high cycle fatigue where low stresses itself, your component usually fails. So one such good example is, let's say you have a rope and you want to break it. So since rope is something, you have multiple like multiple fibers are there. So what you do, you put this rope and just kind of you do up and down motion with a corner, with a sharp corner. When this sharp corner, you put this, like let's say this is a rope, and you put it, you basically rub it across this corner, up and down. So you see, you will maybe some fibers, they'll start failing, and then after some time your complete rope can easily be broken. Because of that, like you are kind of loading it cyclically. Your loading is cyclic, and it may be that you have completely reverse loading, or it can be you may put more compression or more tension. So that way, uh, even before its yield limit, your component will fail. So that's the reason. So that's where you see you have stress life curves which we follow, SN curve. And that's where and again, this SN curve extraction is also very much dependent on the surface finishes of the component, like based on surface coatings or surface treatments, because they are very prone to those like stress concentration factors. Let's say you have some manufacturing defects in your surface, or you have certain notches, or you have certain holes in your model. So that will generate stress concentrations across those areas, and that's where these are kind of quite that will impact more on those components. So this was about the basic understandings or terminologies. I think I have taken a lot of time to explain here. I will just quickly move on to other explanations which I wanted to do. So here I have included a 1D or 2D model. So 1D is basically everyone is following. So I'll not talk much about 1D. Maybe I'll just quickly open it and showcase. So there is a one point which I want to talk about is I mean, most of the students know, they see because of tutorials they are following, like they have created a wireframe and they have run the 1D analysis. So I would say 1D is basically you are oversimplifying your structure. Okay, so as a CA engineer, I mean, as a even or as a judge, I would want you to assess the situation. Let's say many of you might have finished your CA analysis or completed the reports also. So whether maybe during the evaluation phase or during the presentation phase, I would want you to explain why 1D was not appropriate in your case, or then maybe you have explored at least 2D, because in a webinar we talked about it. Okay, so here I have used 1D analysis. I mean, I have done multiple tests, maybe frontal test. You have seen, you can see the deformation. Okay, you can see the stresses, right? So those stresses are also has generated. Now, if you see here, if let's say I have a frame and I have some results are generated. So first of all, I mean, I just want to explain how you can interpret the results. So let's see here, you have maximum is coming as 446, and it is coming somewhere in, wait a second, results. You can probe the maximum, maybe because of P. So you can probe and see your maximums are coming somewhere here. Now you can understand, okay, this is the connection part. So if you're getting maximum here, that is not making any sense. Okay, because somewhere here you will have your weldment. So if you want to see whether this is the correct value, maybe you can further, you can since as of now this is average value, maybe you can make it unaveraged and see how the impact is, whether the nearby components are okay, these are beam section results. Okay, so nearby components have the same value, or what kind of values they are showing. See, if you see here, nearby has 101, and then one point itself has 446. So you can understand whether these results are making sense or not. So that way you can understand, or you can decide, or if in case you still have something, you can always. But anyway, 1D I wouldn't prefer you to perform, because 1D, I mean, there is one assumption which we understand, which we assume that throughout your loading, your cross sectional would not change when you're driving those equations. So 1D analysis, even if you see here, this is a single bar, and when you have a single bar, it will only have one point where you are implying the loadings, because it is 1D, one directional. So based on that, maybe planar things, or maybe in other direction, whatever is happening will not be captured properly. So when you put a beam, or like 1D element through bending, so it will not capture those bendings properly, because when you bend your frame parts, if you clearly observe in physically, your basically your component or your frame would first, it will become oval, your shape will change, and when your shape will change, that means your stress, your plane of application is also changing. But whereas in 1D you will not be able to predict those impacts, or basically you will not be able to capture those ovalization of the shape, Boscher's effects, right? So that way you will not be able to include that in your analysis. That's the reason 1D would not be accurate, or it would be oversimplifying your structures. So what I have done is, I have also created one like frame which is of 2D, like shell element. Okay, and this shell element has 3 to 5 uh, number of integration points across the thickness. So when I say across the thickness, let's say I have 1 second, I will just quickly use this to explain one concept. Like, let's say here you have a frame, and this is the thickness part, and maybe somewhere here you will have your mid surface. So when your part is undergoing bending, so the top surface, let's say if it is kind of you have provided loading to this direction and on the other hand this way, so that means your top fiber will always be in a tension mode and the bottom fiber would be in compression mode. But when you have one point integration, so that means you will not have any kind of stress contours, right? Because you're capturing at the neutral axis. But whereas if you have 3 points across the thickness, so that way you will have like this. So 3 point across the thickness, that means 1, 2, and 3. So I would recommend to have 5 points. Let's say if you have more combined loading, so that way you can capture this kind of stress properly in your frame. So that's the reason we advise to use multiple integration points across the shell element thickness, and you can get this option uh, in your dynamic analysis. If you go here, maybe not here, where is it? LS China, yeah. So if you see in the LS China, you will have this option of including the section. When you right click on it, you will insert the section. So when you insert the section, you will be able to either you can do it from LS Dyna pre. Where is it? Section properties. Section properties. So when you edit, you'll be able to define the integration points across thickness. And when you include it, basically these are the practices which you need to, which as CA engineer you need to follow. Otherwise, there is no difference between me and I mean engineer and a like layman person who just is following the tool. So either so that way you can define it. I mean, these are small things which understanding itself will make us, a little bit better day by day. So that's how you can define the thickness, maybe integration points across the thickness so that you can capture the bending. So I would recommend to do all kind of analysis on 2D model. Okay. Uh, like mesh size, you can capture, you can based on, I mean, recommendation is to capture the stress wave following the, I mean, progressing across the structure. So that way you can define it. But mesh size should remain, I mean, you can do the, mesh convergence study, and wherever your stresses are stabilizing, that way you can follow. Try to, model if in case you have single frame, so try to model the intersections using the way I have used edge sizing. You can define the edge sizing, like you can select the edge, you can pick the edge and right click on it. You can define insert and sizing. So that way, maybe you can define the number of divisions, and with that number of divisions, you will get more uniform mesh across your connections also. So that way, if you see, so these kind of small things you can follow to have more structured mesh to capture. And I would say to go ahead with quad mesh, because uh, this is more this would not be very stiff in terms of your deformation predictions. Okay. So mesh wise, you can use quad mesh. Okay. And which can be, I mean, you can do the stress like your mesh convergence study, and you should be able to talk about it, like why let's say you have picked 10 mm, you have picked 4 mm, maybe in your model you may not be able to generate the difference much. So that means your model is already optimized in terms of mesh counts. So that way you should be able to answer like that you have done these analysis, and this is how the best possible settings as per your computation resources and as per your time. So that way you can define, you can explain those things. Now comes the material part. So you see here I have used so here I have defined bilinear isotropic hardening. So with the tangent modulus of 206 megapascal. So I have yield strength, I have tangent modulus, and I have I have tangent modulus and I have yield. So basically this bilinear is basically is telling, okay, so your one part is linear, I mean your initial part is linear, this is elastic response and this is your plastic response. So this is bilinear type of plasticity. Okay, so this is what the material is used here, and that's where I have defined the material, elastic plastic material, and I have used here three materials. Basically, I want now comes the optimization part. Like I have material, and I like why how to select this material and maybe how to select the thickness. So one way is you can define, you can have multiple analysis performed. Like you can create one more model with this varying parameter, maybe thickness, and with that another analysis you define your material as separate. Or you can do one thing in the analysis itself, in the mechanical itself. Let's say this is surface. I have put 2p. Look, earlier this would be like this. Okay, so what I have done is I have defined the thickness, I have put it as a parameter. And same way I have defined material as a parameter. So when you activate these 2 points here, you will get this kind of window in your main window. Like that way you have defined your parameters. And if you see these parameters, so this will come this way. You will have P2, P4, and you will have, I mean, P2 is your material assignment and P4 would be your thickness assignment. Okay. Now, then it will talk about what would be your output parameters. So then again, you have to define your output parameters. Now my output can be my equivalent stresses. Okay, either maximum or minimum or averaged. Or maybe what I can do is I can optimize for my deformations, or I can optimize for my mass. So that mass may not come here, but yes, you will have another options of minimizing your mass. So you have defined these parameters, maybe equivalent stress, you have put this as parameter, and maximum value of this as parameter. So what you will get is you will be able to see, okay, this is the stress maximum is also your output parameter now. So these would be your inputs, and with this you will have your output as a parameter. I mean, it is also get impacted. So then what I have done now, I have when you okay, now when you click on this, you will get this window which is table of design points. So if I close this, I will get this kind of window generated. Then you can define, okay, this is my assignment for material, and this is my assignment for thickness. So I can vary my thickness also, I can vary my material also, and these are my design points. And once you evaluate this, you will be able to, I mean, I have computed only for one design point. So you see I have equivalent stress which is changed. For others, it may not change, but okay, now I think these all are computed. So if you see here, these all are like computed, and they have different different answers or different values for different conditions. So that way you can optimize your design, or you can understand what would be the effect of maybe varying the thickness or changing the material. So important thing is you have to define those materials in the engineering data, and you should be defining those with actual values or the parameters which you have at your disposal. So this is one way of doing the optimization, which can be done with a parametric approach even in the mechanical itself. Another way is you have there is one tool called OptiSlang. So OptiSlang is also lying here. You just have to optimize. You have to just drag optimization and put here this way. So when it be dragged here, you will see this kind of window. And when this kind of window comes, you will be asked for 2-3 options. So let me see whether again it will ask for it. Okay, so when you drag and drop it, it will ask, okay, parameters are your thickness and material assignment. Okay, and it will ask whether this thickness would be a constant value or it can be a continuous value. So when you are defining it as continuous value, it will ask for a range. So you have defined that range also. And for structural, it is kind of a discrete value, like whether this model or another model. So that way you have defined. Now it will ask for the criteria. So what would be my criteria? My criteria would be to minimize the maximum stress. This is just an example. So what I have done is I have put picked this as a response, and I am just putting as this criteria as minimized. Either I can maximize it or minimize it. So for mass also we can minimize it. So when you define this minimization, it will ask for how many number of iterations you want to run. Then so just for the demonstration purpose, I have only put 5 runs. So it was taking quite a lot of time to run it. So that way I have defined 5 iterations. And once you define all those iterations, okay, maybe this, if you see here, maximum number of design evaluations. So you have put 5. So it will run 5 iterations, and based on that iteration, it will try to minimize the mass. So you minimize the stresses. So if you see here, with the value of thickness, it has reduced it has kind of minimized your stresses. So in the 5 iterations, you have got 218.424 is your final minimized objective. So that's how you can define the optimization, and you can do the optimization on your components accordingly. And I mean, maybe once you start following the optimization, you would be able to understand, okay, this much of mass is being saved, or that is how robust my design would be. So I think I have briefly touched upon optimization. Anyway, there is no theory part to explain in optimization, because optimization is something you have, like you have parametric variation, and based on that parametric variation, what should be your response. This you can do manually also, like anyway, understandable, like you can have multiple analysis and instance launched and run, or you can do it in a proper streamlined way where you will get all those outputs compared in a single way. And I mean, here result will make more sense. Now, why the optimization? So we have two kind of optimizations. I think that will not be here. So either it can be direct optimization, which we have done, where we are just simply running the iterations, varying the thickness or assignment, or we can have one more thing called meta model. So basically from machine learning or algorithms approach, we can kind of create a certain surrogate models which would further reduce the run design iterations which are needed. I mean, that is more in-depth thing which may not be of very useful to you as of now, but I mean, you can give it a read. Maybe you can utilize it in your optimization purpose. So this was all what I planned to cover today. I hope like some of the value addition I have done today. And if you want to understand more in depth about FEM analysis, so there is a very good book called Finite to Infinite by Nitin Gokhale, which is I mean, the language is very easy. You can just follow it in your day-to-day life, and you would be making a difference in your understanding. Rest, if you want to understand more depth or in-depth finite element method, those NPTEL lecture series are there, I think, from IITM, that you can follow. And a very good book from KJ Bath is also there, which can be followed. I think that is all from my side today. I kind of have squeezed a lot of content or a lot of explanation in this short session, but for any follow-up queries, for any discussions, you can always reach out to me. You can take my connects from Aditya from alumni team, and maybe with interest of time, I will just stop here. I will take 1 or 2 queries, and then maybe we can close this. Thank you, everyone. Yeah. So maybe I'm open to questions.
Teams, you can put your questions in the chat box.
So I could see a question where while doing a static analysis, how can we find an accurate FOS correctly? Like it always shows below 1. So what I would suggest is when you are doing the analysis, you should try to see whether those deformations, let's say, I will just quickly showcase, I will try to explain this with an example. So maybe in my model, I will have one, okay. So yeah, maybe in this itself, if you see here, this is a dynamic analysis. And if you see, I mean, this is a dynamic analysis where FOS will not make any meaning. But you see here, when this model is being buckled, so if you see the complete member is being buckled, right? So when this member is buckled, that definitely would add in your FOS. Your FOS would be very small. So what you can do is you can try to see whether some local bucklings are happening in your model. Maybe somewhere, we have small interfaces. Let's say in this model, maybe let's say in this area, the top triangulation is quite rigid. That's the way it is not deforming. But sometimes you see deformations in this area itself. So that also would lead to lesser FOS. So first of all, you need to understand whether the deformation is localized or not. If in case it is localized, you can further triangulize it and you can make it, you can make it more distribution worthy. Your structure should be in such a way that it can distribute all the loads which are coming to other locations, or it can absorb it appropriately. Okay. Can we use surface model here? So surface model is basically the 2D body. Yes, you can use surface body. So preferred mesh quality would be, I mean, your mesh should be, the flow should be captured. I mean, your deviation should not be there. Like you have multiple quality criteria in terms of, mesh. So those, I mean, those are pretty standard value which you can get it from internet, but try to see your out of plane, deformations or out of plane mesh quality should not hamper. So mass optimization, I think I would give some references. From there, you can try to understand it, because in interest of time, it is quite difficult to explain it in detail. So in dynamic analysis, basically, what are the basically results which are important? I will just quickly showcase it here itself. So let's say generally what we do know, implicit analysis, there is a simple difference between implicit analysis and explicit analysis. So your implicit, generally what it does know, for each and every time step, it balances your input and output force. So your force input is equals to force output. So that is what is called as a convergence. So whenever your convergence is happening, your analysis will be accurate. Whereas in explicit analysis, what happens? It basically checks for the energy, because here there is no convergence check at every moment. Like for each and node, your forces will get converged, your movement also will get converged. Like it will be equated to zero. So that means all the forces would get balanced and all the moment would get balanced. When this balancing would be there, you will not get any, you're not getting any errors accumulated in the results. But whereas if you talk about explicit, so these balancing would not be there. So what it does, so you will have like your total energy of the system, you will have kinetic energy. So basically the energy which you have given into the system should be absolutely converted into internal energy of the system. There can be a small gap, which is because of your contact parts which are coming into the picture. So whenever you do the analysis, explicit analysis, always try to see whether your convergence of KE to IE is appropriate or not, or whether any kind of contact energy is rising or not. So first check should be to check the energy conversion. And when the energy conversion is accurate, or the phenomena is captured properly, so basically after energy check, you check for the animation. If your phenomena is captured, you can read those deformation and stresses results. I think those would make sense. So meanwhile, what I would do now, I would keep replying to these queries which are there in the chat. Maybe Rohit, you can take over and you can start your session.
Thank
I think.
you, Meg. I will share
Yeah.
my screen.
Please go ahead. Yeah. Rohit, thank you. Sorry for taking some
No
of
issue,
your.
no issue. Is my screen visible?
Yes, I could see your screen. Rohit, over to you. Thank you.
Okay, thank you. So a very good evening to all. I hope you enjoyed the last session. So now we'll discuss about the CFD. So in generally in Maha we see a lot of students are doing a lot of CFD structure simulation, but hardly few students are doing CFD simulation. So I will give you introduction about the CFD. What is CFD, and what are the application where we can use for Baha this our card, as well as then I will showcase one examples how we can run the simulation for our vehicle. Okay, so first thing, what is CFD? CFD is nothing, it's a science of predicting fluid flow, heat and mass transfer. So in our car, what we are doing, we are predicting the airflow, how much air drag will be there. Okay, how much forces it will impact on our on driver or on the car. And we have when we have the engines or some battery at background, we have to cool them also. So the air circulation is very important. So we should know how the fluid is moving and how it is behaving. So to predict this fluid behavior, we solve our Navier-Stokes equation, or we can call it as conservation of mass and momentum. So mass is continuity equation, momentum is our Navier-Stokes equation. If we are adding heat to it, then we'll solve our energy equation. So the more physics we solve, the more number of equation we'll add on, and we'll keep solving our CFD. Like we are predicting the fluid dynamics with the help of computers. So it's a virtual environment. So we call it as computational fluid dynamics. CFD provide lot of information. When we are doing any simulation, we can find out the distribution of pressure, which is very critical, very important. Okay, where we have the maximum pressure, where we have the low pressure, where is the stagnant zones. So all these kind of zones we can identify with the help of contours. Then we can find out the velocity also. At which velocity, if my air speed or the my vehicle speed is this much, how much air, how the air will flow. So velocity profile also we can identify, and the temperature also. Like in CV we are doing the cooling of CV part. So how, what kind of air velocity we can provide so that it keep cooling the part. So generally that comes under internal flow. So when we are doing external flow, there is more important forces like lift and drag. Because suppose if your lift is very high, what will happen? The front air will try to put more forces on the vehicles, and it will try to lift the vehicles, which is very dangerous. So we should have the lift in such a way that the force should be more towards the downward direction, so that our vehicle keep balancing. Okay, same way, if the drag is more, we have to burn more fuel. So we have to work on these parameters whenever we are working on the external aerodynamic system. Same way, we have other application like multi-phase gas liquid gas. If you're using some battery for e-Baha, you can see we are using batteries as a power source. So how we can solve them? So we are nowadays we're using phase change material, PCM part. So those kind of multi-phase simulation also we can work, and there are a lot of things. So we'll cover which is more related to our part. So CFD we use in all aspect of engineering, whether we have to create new design. If we have some development cycles from different design variables, we can see which design will give us the best part, how we can optimize that design also. And if we got some error, so even if you see, if you're doing racing, you are doing manually, so if you get some error in the vehicle or something falls down, you will do troubleshooting. Same way in our design also, through virtual simulation we can do the troubleshooting also. If you're getting some unexpected value or more drag value, we can change in the design, and we can see how we can reduce that uh, error also. So overall, CFD will save your cost and time also. So you can check in your simulation, then go for the manufacturing part. Okay, first check your design, then go for the manufacturing. So you can see in this car, generally we in Baha we don't have that very high speed vehicles, but if we talk about the FSA car, so the where drag plays very important role. But here also we can reduce the drag, so can have the maximum efficiency. So overall it will save our time if we go with the virtual simulation. These are few examples, like other kind of simulation also we can perform, like turbo machinery, compressor, IC engine combustion, two phase heat and mass transfer, then heat exchanger. So you have radiator in your vehicles. If you're fixing that, then how heat is transferring to make the engine cool. That also is very critical. So you can do those kind of CFD simulation also there. If something is rotating part is there and you want to do CFD simulation there, you can perform the analysis of that part. Generally, we can do the tire simulation also, but as of student level, we are not performing that much. But if something you have something rotating part, you want to do analysis of that rotating part, where the flow plays very important role. Either it's a air or it's a water or any fluid medium. Then we can perform the CFD simulation there. So these are kind of few examples application where we can perform the CFD simulation, like internal flow, whether the flow is laminar, turbulent or multi-phase flow. We can perform some internal flow simulation, external flow simulation, battery simulation, combustion simulation also if you want to perform optimize your engine. So for that also we can do the CFD simulation using Ansys Fluent tool itself, as well there is a tool another Ansys Forte where we more focus about the combustion part. So most of industries are using optimizing their engine power with the help of simulation only. Then heat transfer, so you are putting your uh, shade on the driver, so how much radiation it can bear, because when you're driving in the rest condition, okay, there is a lot of heat will come. So how, what kind of metal we can apply, how much conduction convection will come, all those things parameters you can identify with the help of CFD simulation, and you can make your vehicle more better way. So the shade material or along with the design input requirement, how you can make the heat more transfer. So how much sun radiation will come, how much temperature will be there at particular location when we are putting brakes. So we do structural analysis along with, if I'm putting some coolant, okay, hydraulic cooling, if I will add there, so how it will help me. So we'll increase some weight, but the efficiency of the vehicle will also increase. So this kind of simulation we can perform on our vehicle. So we have Ansys CFD product. So mostly in, if you have to download the student version, and if you're already in your campus, we have the Ansys tool, we can perform our BAHA simulation on Ansys Fluent. So this is general purpose tool where we can perform almost all kind of simulation tool, but there are specialized tool which are particular for different kind of application. I'm just giving you overview. As of now, you require only Fluent part. Okay, if you're working on some turbines, turbo parts, or turbocharger are there. So mostly some students we have seen they are putting turbochargers, so you can perform that simulation in Ansys CFX as well as in the Fluent part also. So this is next part, we have Rocky, mostly used for the particle simulation. So how the tire is interacting with the part sand, so that kind of simulation also we can perform with the Rocky. Then Forte for the combustion part. Chemkin Pro is for chemical engineers related to combustion only. Fansep ice, as of now, not required in your simulation, but related to ice formation. So generally, we are creating drones. So when drone go for height level, we are checking that how the ice is forming and that. Then next we have Insight, which is post processing tool advanced, where we can visualize the real behavior. So here you can see the contours, but in actually, if you want to see the water in proper animation, we can visualize in the Insight. So this is advanced tool to get better visualization of our results. Then last we have Polyflow. So we will find lot of plastic parts in your vehicles. So related to plastic mold, how the mold will create and how the formation will take place. Those kind of simulation we can perform with the Ansys Polyflow. Now we'll go with the CFD flow chart. So how we are doing the simulation and what is the procedure. So if you see, first we have to identify our problem. So what I'm going to do, okay, what kind of simulation I have to perform. So if I'm looking for the external aerodynamics, okay, so in external aerodynamics, we have to identify what is my major goals, whether I have to reduce the drag or uh, reduce the lift. So both we can work together also, or separately we can major focus also. If you are looking for the heat transfer also, then based on that parameters we have to identify our domain, and we can clean up our CAD model also. So we'll identify those domain, then we'll do the pre-processing. So in once we can create our CAD model or as well as we can create in our space claim tool also. There are three tools for modeling purpose: design modeler, space claim, and discovery. Nowadays we are using discovery because it will give us more faster optimization, like how without providing meshing and all those parameter, I can easily visualize how the flow will happen. Okay, that is generally using in the design phase. If you have other tools like SolidWorks or any other tool, you can bring that CAD model to the space claim, and then you can repair that CAD models. Mostly students, what they prefer, they download from the GrabCAD, and then they will do the simulation on that part by changing, putting their parameters, and they will see what kind of results they are getting. So then we'll do the meshing part. So we'll convert our CAD model into mathematical model, and once we apply our mathematical model to the solver, we'll apply our physics, we'll give our boundary condition, what are my inlet velocity, what is my outlet condition, how the tires are rotating, at which speed they're rotating, or if the air is flowing, at which speed it is moving. So those inputs will provide, then we'll solve our equation. So once we compute our solution, we'll check the results. So if we feel our results are okay, like generally we check the physics. We know fluid flow from high pressure to low pressure, and when there is a low pressure, there will be suddenly high increase in velocity. So those physics, if we are getting, and if we are okay with our results, then we can go with the prototype testing. Okay, if you are not satisfied with the results, because the solver will give you always some output, even if you put some condition, it might give some output based on the input condition, but we have to check our results whether those results are right or wrong. So this is like one example. Mayank sir was talking about the optimization. Same way, this is was the model where they have optimized this design with the thermal profile of windshield with respect to thermal point of view, and they have optimized this design to this. So we can see we can reduce lot of material, and we can reduce our vehicle weight also. So that is a very big uh, saving for cost. Okay. So if we see with respect to tool wise, so modeling we'll do in the space claim, then we'll convert our CAD model into mathematical model. So generally we call it as meshing. So meshing, for meshing we have 4 tools: workbench meshing, fluent meshing, and TurboGrid, and ICM CFD. So generally students are preferring workbench meshing. So fluent meshing is more advanced, I will say. So if you're working on some turbo machinery part, then you can use the TurboGrid tools. And if you're looking for the structured mesh, where we have a lot of convex design and we have a lot of ample time, then we can go with the ICM CFD. Mostly research scholars, they are using ICM CFD. So you can use both workbench meshing as well as the fluent meshing. But fluent meshing have major advantage, like we can generate good mesh quality within less mesh count. So when we have the less mesh count means we have to run it for less time. So the computation time will be less. Okay. Then we'll set up our condition in the solvers based on the problem statement, and then we'll check the results. So we have option to check results in the tool itself, as well as there we have other post processing tool also inside CFD post also, and then we can optimize our design also. Just a second. Sorry. So we can do the post processing part also. Um, as of now, in our vehicle, we require some optimization, but we have the option also. We can develop our flow chart also, or we can use our code also. For that, we have Ansys customization suite also there. Just like we have Google Play Store, we have Ansys Store also, where there are a lot of sold examples are there, which we can bring that physics to our workbench, and further we can do the simulation, and we can add on those physics also. So sometimes there are piezoelectric parts, some other thermal part simulation, solar part simulation, which are already case examples are there, which we can bring to our tools, so that we can go through Ansys Store, and we can download, and we can customize to our workbench. Now we have workbench multiphysics, which is very important. So we are doing FE analysis. Okay, now we are doing CFD analysis. If you want to see the effect of air pressure and want to see the deformation, then we can do the fluid structure interaction. So when we want to do this kind of simulation, we require a workbench that we can solve the both physics together. So we call it as multiphysics simulation. So now we'll talk about the external flow simulation. So that is, we have to understand what is how, actually what is happening. So generally in simulation, in reality, what is happening? The vehicle is moving and air is constant. Okay, but in simulation we do the reverse. What we are doing, we are keeping the vehicle as constant, and we'll move the fluid thing. Okay, so external flow refers to a situation where our body is completely immersed inside the fluid domain. So like you can see, we have a train which is completely immersed inside the fluid domain. So we have to create a fluid domain to predict the flow behavior around the vehicle. So when fluid is passing, there will be a lot of forces will act on the body. We have to find out how much forces is acting at which location, because sometimes we have very high forces. Even if we are looking for the thermal simulation, okay, if we are adding some heat, generally if you say simple, internal pipes are there for cooling liquid jackets or those. If they're very high, so the stresses, thermal stresses will be more as compared to structural stresses. So we have to consider the FSI there. Okay. So they might look very simple. So external flow simulation, you can take one example. We have simple bowl, circular bowl. When the Reynolds number is around 9.6, there is no separation. And when if I increase my Reynolds number further, you can see there is a steady separation. And if I increase little further, so you can see there is hardly little change in the Reynolds number, but my flow separation is unsteady separation, and there will be lot of wake regions. So these wake regions will generate lot of vortexes, wake regions. Okay, so that's how we see through the external aerodynamics that we can reduce. Now we'll go with our modeling part. So you can have a model of your design. So generally, when we have car model, what we create an enclosure outside the domain. So just like so that the complete body could be immersed inside the fluid domain. So also when we're creating the enclosure, the tire will have sudden contact with the bottom surface with the ground level. So there might be chances that if we have the sharp edges will be there, and that will be contacting with the ground surface. So the mesh quality can be reduced. So generally, what is the approach you should use whenever you're doing simulation? Always try to give some fillet near to the tires. So that will help us to reduce our uh, uh, quality. Okay, it will help us to get more good quality, and skewness also will be near to 0. So also we have observed like a lot of students are just simply creating the enclosure and running the simulation. So that will give some value, lift of drag and coefficient, but it will not be that much accurate. So if you want to optimize the real how actually the flow is separating, where the boundary layer is forming, for such case scenario, what we have to do, we have to create body of influence. So body of influence are just created extra part which are used for defining the mesh to do the local refinement. So near to the tires, we have to capture the flow. Near to the helmets or the passenger driver is there. At those parts, we have to create the verified mesh. So we create the body of influence. So simply with the sketch, I can create the body influence. So for this case, we have created two body of influence. One which is creating very fine mesh near to these vehicles, and second where we know the wake region will be there. So from the back side to the vehicle, so that will have less mesh count, because suddenly the small mesh to the higher mesh ratio should not be there. The mesh should be defined gradually. So to for that we created two boundary of influence. Now many students have we have seen that they're creating enclosure, but they're not sure what size they should consider. So suppose we have a car of 3 meter. So I should take the backside, the outlet from where the air will come out. So it should come out stationary, okay, with the stable condition. So it should have minimum 3 times of our model size. Same way, upward direction and the front direction also should be of 1 time of our CAD model size. So in this model, what we have tires, we have front wings, we have the rear wings, we have the chassis. So all models you can create, you can give them naming, and you can create the design. For this simulation, what we have done, we have imported the CAD model, we have provided the fillet, then we created the enclosure. After that, we have created the body of influence. Now, since we know our domain is very big, so what we have done to reduce our computational time, we have make it half. So we have make it symmetric, because the geometry is symmetric. So whenever you see your geometry is symmetric, we can reduce our computational time. So we can cut it from the center of the plane, and we can make it center part. So we have finally used this design as our part. Uh, since the vehicle is moving, it will move. So the what part we have, the wheels will rotate. So to give the rotation coordinates, we have to find out in the tool itself. So from in space claim itself, we can find out the what is the my center of axis location. We can create the center of axis also in the vehicle tires, and we can measure from the which was there from the real when we imported the models, because the origin point could be different for the tire and for the our complete design. So we can find out our center location to give the rotational velocity in the setup later on. Then we have to provide the naming. So for this our case, this is my inlet, right hand side is my outlet, uh, this is my tunnel walls, and downside is my ground plane. Okay, so in our case the ground plane is moving and the wheels are moving. So we have given the name to all parts, which is because naming is very important. Based on the naming only we can provide some boundary conditions. Then once we complete our modeling part, we'll go for the meshing. Okay, so we have if we go with the workbench meshing, we can go with the 2D and 3D. So till 25 there was a 3D modeling meshing option was there only, but in 25 R2 we can go for the 2D meshing also in the Fluent meshing itself. So that's why most of students were preferring workbench meshing. So now in Fluent meshing, if you have something 2D model you want to optimize, you can do that part also. So we have two options. Like you can see, we have a clean CAD model now. Suppose if you have some dirty CAD model, so in that case we can use the Fluent torque meshing. So we don't have to repair that much without wasting time. We can go with the meshing and we can use the Fluent torque meshing. But for this case, we are using water and we are providing some local mesh control, that is at the boundary of influence 1 and the boundary of influence 2. Also, since we have a lot of curvature surface in our domain, so we are creating the curvature control also in the meshing. So I will show you in the tool how we are given those inputs. Then we'll generate the surface mesh, and then we'll generate the boundary mesh, that is in the boundary. So you can see in this, right, near to this region the mesh is very fine and gradually it is increasing. So it is not very fine then suddenly big size. So this thing you have to keep in mind when you are doing meshing. Okay, wherever we have the objects at that region we should have fine mesh, and in the enclosure you can do some coarse mesh also. Then and last we'll generate the volume mesh. So this is the meshing settings we have taken. So we have we can import the model. So if you have the model in mm size, you should select the mm units. If you have created your model in meter, you should select the meter as a unit when importing the models. Then we'll apply local sizings. So generally student prefer they don't apply local sizing. So that is the we have observed. So they will just simply click on the mesh and we'll go with the naming and directly we'll go to the setup. So always go with the local sizings, and that's why to do the very fine meshing at the local, we created two boundaries. So you can see in this region, near to this region, I have created very fine mesh as compared to outside region. So these are, then we'll describe our geometry. So there is a standard flow chart in the Fluent meshing. You have to follow step by step. So once we apply the local sizing method, then we'll describe our geometry. We'll update our regions, what kind of regions we have. Then we will add the boundary layer. So boundary layer is the inflation layer. So whatever inflation layer we create in the workbench meshing, here it is boundary layer. So boundary layer is very important to capture our flow near to the walls. So how the boundary layers are there. So y plus value is very important that we can optimize. So based on the velocity parameters values, you can find out the y plus value also. So generally you can go with the basic course first initial case, then you can see if your setup is correct, then you can go with the fine mesh, because generally if we go directly with the very fine mesh, what will happen, computational time will be very high, and sometimes you get the divergence also, and you can get sometimes you get lot of time to run it. Yeah. So first go with the little bit coarse mesh size, then you can go with the reduce the mesh size. Once you see your setup is correct, for last turn you can give the more fine mesh. Then we'll generate the volume mesh, and if you see the quality is not well enough, then you can improve the volume mesh also. So there is an option in the Fluent meshing where you can give the skewness value or the orthogonal quality value in the tool, and you can the tool itself will create the fine mesh with respect to that parameter. Then we'll go to the setup. So let me show you the tool. So I have one case already open. So this is the geometry I will show you. So this is workbench. You can see we have the different tools, just like we have discussed CFX, Fluent with Fluent meshing. So if you're using Fluent meshing, you have to take the Fluent meshing. Okay. So if you're using with the workbench meshing, you have to take the Fluent part. So I'll show you the structure. So this is like half model reduced. Okay. So we have, so the parts which are not activated. So generally whenever we are doing our external flow simulation, we deactivate the models. So I have suppressed for the physics. Either you can uncheck them or deactivate them also, because when we create enclosure, it will imprint the faces of all our CAD model to the enclosure. So solver will assume there is a object here, vehicle, and it will calculate on those walls. Okay, so that's why we have closed the uncheck this part. So there we have front wing, wheels, chassis, rear wing, and now we have enclosure. That is our fluid domain, and we have given the names in the groups. So naming is very important. So whenever we are doing fluent meshing, the naming should be done in the space claim itself. Later you will not have option to do in the fluent meshing. If you're doing workbench meshing, then you can do the naming in the workbench meshing itself. So this is the inlet we have. Then we have outlet opposite side. These are my tunnels walls. Then we have symmetry at this side. That means same thing is there towards that side. So generally that will reduce the computational time. But if you want to use for the post processing, we can visualize the complete vehicle also. So that I will show you. Then we have ground that will be moving. So this is a boundary of influence, far field, then wheel radius, all those things. We are given the name so that we can find out the forces on all these parts. So that is our first step, defining the goals. So what is our major motive? If I want to know the forces, where I want to know the forces. So those names we have to give here in the space claim itself. Now, second, then let me close this. Let me open another part. Then we'll go with the fluent meshing. So once your model is done, modeling part, you can use it for further simulation. Suppose if you want to do FSI, same model you can use. In that FSI, you have to suppress the enclosure part and your part will be active. So for structural analysis, you can simply drag it and drop it and you can use the same model. So this is how we do the FSI simulation. So but now we're talking only about the CFD. So we are doing CFD simulation only here. If you have any question up to this point, please you can put in the chat box. Just a second. It is there. So remember, I have created the model in MM. So you have to always right click here and check the properties. Sometimes we get the queries that, sir, we have created the model, but it is not showing in the fluent meshing. So generally, what is the issue there? So when we are selecting here, by default, the unit will be meter. So when we go with the meter, it will not able to select the our CAD model. So always change the units to in which unit you have created and in which unit we want to create the mesh. Okay. Now, after selecting the properties, this tab will come and you can select change from here meter to millimeter. Since already have done, now I'll show you the edit. So I'll not do the meshing since it will take time. So I'll just showcase you the option only. I think close this first. Edit. So we can edit the fluent meshing also. If we have done some meshing part, we can edit that part also. So it will take some time. Okay. So just we have to wait. So this is our domain. Okay. So there is option just like we create the section plane. Here also we have the option insert clipping planes, and you can select the location in which location you want to visualize the part. Okay. So we have option first we'll import the model geometry. So there you can, if you want to work in the standalone system, so there's an option I can simply work in the standalone system also fluent, and you can directly select there whether you want to work from the case and setup with the solution, or you want to work on the meshing part. So you can select there, and you can select the directory where you have the file. So once you can go with the that part also, as well as you can go with the workbench. So we have two options. Now, generally, when we import geometry, we can select the file here. Since we are coming from the workbench, it will select automatically there. Then we have option local sizing, whether you have to add local sizing, no, yes. If you select yes, we have option. So we have applied the yes, and we have selected the body of influence. So at that our body of influence, we have selected the type, and there we have. Since we already given the name, we have given the part. So like this, we have to create. Then describe geometry is also very important. So we'll generate the surface mesh once we do that part, and it will show like what kind of particle size we have. Okay, it will show, and you can see the parameter also. Then we'll describe the geometry. In this case, when we have external flow simulation, when we have enclosure, we have both domain, fluid as well as the structure. But if you see in space claim, we have suppressed the solid domain. Okay, don't require and we don't have. So as of now, for this case, we are taking only fluid region. But in case when you're doing some battery simulation or some other parameters where you have the solid part is also there and liquid part also is there. For such case, we'll use the C option, fluid region and the solid region. And there might be chances like we have internal flow simulation where the fluid region is not there, hollow pipe, and I want to extrude the fluid region. So for such case scenario, we use the solid region. So as of now, we are using second option. Then we'll update the boundaries. So the parameters. So these are the names. That's why it is important to define the names. So what are the walls? What are the inlet and outlet? If you provide the name, the tool will take automatically. If you feel you have to change, you can select the arrow and you can change the parameters, boundary types, or any other name you want to give, you can edit here also. So we have given the complete naming in the space claim. Now here the boundary type are selected automatically. If you want to change, we can change here also as well as in the that part. Now region, how much region we have? One fluid region. So if you have multiple fluid region, we can provide the different fluid region also. Then we have boundary layer we have added. So with respect to last ratio, okay, to refine the mesh at this particular walls. Then we have generated the volume mesh. So in volume mesh, we have option. I can go with the polyhexacore, polyhedra. So different option meshing method we have. So you can select the polyhexacore. So that is widely used for capturing the our external flow simulation and VEX regions. And then we have improved the volume mesh. And here you can see I have given the quality limit to 0.1. So with respect to that, it has okay. Which part we can delete as they will not affect airflow like. So if you want to delete some parts, you can delete. Okay, but like in this case, what we have taken, we have considered the full whole aspect. Okay, outside enclosure where the major force is. Backside also you can delete some engines, all those parts if they are not open. But if they are open and directly air is coming, so there will be cases where the pressure will change. Okay, so those things can have some recirculation region also. So depends on how you want to do the CFD simulation there. Just a second, it is taking. So it is taking time. I will just open the previous one. Okay, so directly you can switch to solution and you will come to this tab. So meshing is very important. If you see the most of results in CFD, the meshing is very critical. So whenever we have flow, to capture the flow accurately, we should have very fine meshing. You can scale the model if you require, but if I don't think your model are that much big. We have, if you see this case, we have taken this model size as 1 meter. In the length is 3 meter, height is 1.2 meter, and width is 1.4 meter. But still, you want to scale down. You have to scale down the parameter also. Okay, because with respect to that, you have to reduce the velocity also. You can do that part if you want to reduce the computational time. But for reducing the computational time, what we have done? We have done the symmetric part. This is so here we once we open this, that is general setup. Since our flow is not that much highly variable dependent on the density, so we are using pressure based solvers. Okay, and flow is below Mach number 3, we are using pressure based solvers. So, and we have two option. I can find out my results of fluid properties with respect to time as well as the final results. So generally when we have initial case of, we can go with the steady state, but when you want to capture particular at particular time, when we have transient condition, that case we use the transient condition. So when we are studying the flow with respect to time, we go with the transient case. As of now, we'll go with the steady state. Then in models, our viscous model is very important. So based on our velocity, like we have taken input assuming 20 kilometer per hour. So with respect to our inlet diameter and our fluid properties, air, viscosity. So I will find out the Reynolds number. Based on Reynolds number, I will check whether my uh, velocity lie in the laminar flow or in the turbulent flow. For our case, where flow is turbulence. In turbulence also, we have different models like K epsilon, K omega. So when we want to capture the flow separation, K omega is recommended. And to capture the near to the curvature parameters, we are enabling the curvature correction parameter also. Then these are the other parameters which are controlling our constant parameter of our equation. Okay, so more you want to know, you can go with the help and you can go complete theory, which kind of model is useful for which kind of analysis. Okay, so for large eddy simulation is generally used by the researchers who have a lot of ample times to capture the each eddies how it is forming. Okay, so as of now we will not change. Then since we are not looking for any heat transfer in this case, we are going directly with the energy. Sometimes we have the mesh file. So what we can do, we can simply go to the display and we can check the mesh also. So like I will show you here ground. So whatever the you want to display, it will display. So you can check the mesh file also, what inputs we have brought. Okay. So if I check the here also we have option. Instead of like this name, I can go with the surface type only. So I want to select only all walls, select display. Okay, I have hidden the symmetry. Tunnel wall I am hiding. Now inlet and outlet. So we'll get better clarity of view how the flow is there, because when we are doing external flow simulation, it is very important to know the direction of the flow. Based on that only we'll provide the our lift and drag. Okay. So now this way you can check your import model. Now you can see what I have. I only half model, but if you want to visualize the second part also, just go to symmetry display. It will display here at like this. But if you want to see in reality, you have to go to view, go to views, and there you can select the mirror plane and apply. So I will hide this symmetry plane. Now apply. Now you can see I have created half model, but I can visualize my complete CAD model. So with the help of view symmetry, under the view option, view mirror plane, it will create the model, but it will not add any computational time. Okay. So that generally we do after the running the simulation to check the post processing part. Then we can go with the materials. So we have by default air in the fluid materials. If you want to add some material, we have the option. Just like engineering data we have there in the structure, same way in CFD we have the fluent database. So we can add here any material. So with respect to each version, the materials are increasing. So you can add any material, fluid material. And if some material is not there, simply you can type the name here, chemical formula. If you know, if you don't know, you can leave the space and you can give the properties. Since we are looking only for the flow, if I enable the energy equation, the energy parameter will turn on. So I will just show you equation. Okay. Then specific heat thermal conductivity. So what kind of models you are solving with respect to, you can first you have to enable those models, then the properties will come automatically. As of now, we don't require, so we can turn off this equation. Then these properties will change automatically. If you want to have different density, like it is compressible flow, you want to use ideal gas condition, then you can use like this also. But for this, we don't require, so it is our normal part. Then for this case, we have option cell zone condition. Now we have taken the material, just like in FEA we have the engineering data, there we select the material, but after going to the model option and selecting the geometry, we assign the material there. Same way in the cell zone condition, we assign the material. So at the enclosure, by default is air. If I have other material, I can assign that part. So I'll just show you that option also. Suppose I have air, if I will add water liquid also. So instead of air, if I'm flowing my vehicle, riding my vehicle with inside the water domain. So you can add the water liquid, copy, close. So you can check water liquid is added. Now we have option, I can change my enclosure to water liquid. So any kind of gas is there or some other uh, in other kind of flow is there, you can add those liquid there properties. Okay, as of now we don't need to change. Then we'll go with our boundary conditions. Same way. So here we'll go with the zone type. So inlet, we are giving the velocity. So since the vehicle is, we are not moving, we instead of moving vehicles, we are moving the air. So we are given the velocity 20 meter per seconds. So at this case, the turbulent density is around 0.5%. So we are keeping viscosity ratio 2. Same way, if we enable those models, thermal, other models, those models will be enabled. Then we can provide those parts. Suppose this is my normal air. If I'm giving some coolant air or hot air, because if I'm looking with respect to temperature, if then thermal input I can provide. So for that, I have to again enable the models. So those things are very important when we are using those parts. Same way at the outlet, we are keeping the atmospheric condition. That is, you can check in the operating condition 101325 Pascal. So that is equal to 1 atm atmospheric condition. So you can change that parameter. And so we are keeping gauge pressure as 0 because gauge pressure measure above atm pressure. Okay. So now close symmetry. This is symmetry. We have to keep symmetry only. Then these are my walls. So we have given chassis other parts as a no slip condition and stationary. So I'll just show you no slip condition uh, here and the stationary wall. So ground wall is moving. So we are given as the translation motion to the ground. Translation x direction in positive x direction you can see, and speed is 20 meter per second. Same way, then we have wheels, rear wheels and the front wheels, they are moving. So we are given them the rotational velocity. So they are moving with the road. So this axis of origin we have find out from the space claim, just like I showcased you the slide in that one. Okay. So this from those coordinates, I have given those coordinates, and with respect to the velocity, okay, we have taken out the parameters. These, okay, it is not there. So angular velocity we generally find initial speed, the inlet speed we have given divided by the wheel radius. So that we can find out with the angular acceleration radian per seconds. Okay. Then we have applied those boundary condition. Then we'll go with the methods. So for second order discretization, we are going with the second order. So it is like kind of Taylor series form. The more higher order we go, the more accuracy we'll get. Okay. So generally, sometimes there are a lot of scheme also. Uh, Pressure velocity coupling. Simple means pressure will equation will be solved separately and velocity scheme will be solved separately. When we're coupling, both will be solved together. So for this kind of simulation, we use the coupled scheme and second order scheme. Then controls, these are the relaxation factor to control our simulation. So we're keeping by default. Then comes the major important part in the extreme flow simulation. So we have to find out the lift and drag forces. So you have to go to report definition, right click, new, force report, drag and lift. Like this you have to create. Then you can name them and you can select where you want to know the forces. So as of now, I want to know the drag forces at this location and the direction. So you can see here, my air is coming from this direction. So the drag will be in positive x direction. So I have kept 1. If my direction is in air is coming from this direction, then drag will be in towards air direction. Then I will put -1. Same way for the lift also, lift will be in positive y direction. So by default they will come like this. But if you have something different axis of rotation, you have to find out this at which direction the forces will act. Okay. Then we'll monitor residual. So what kind of equation we are solving, what are the convergence criteria we can enable. Sometimes we are not getting, we are getting convergence very fast within 5 to 10 iterations. So we can increase the convergence criteria. So mostly in battery simulation cases, we observe this. So minimum we should have 0.3 e to power 3, for energy e to power 6. Rest we can vary with respect to our requirement. Okay. Then once we create this part, this plot will be created. Then we'll initialize our solution. Initialization means initial value we are giving. So in boundary condition, what we have done, we have given the value at the inlet, at the outlet, at the walls, but at the grid, we have not given any value inside this enclosure domain. So we are giving some initialization value, initial value to start our calculation that we do in the initialization. So for initialization, we have the hybrid initialization and the standard. Standard means when I want to compute from particular area location, and hybrid will takes average value. So here we have done the hybrid initialization and then we have done the FMG. So when we have this kind of complex flow, we simply go with the FMG initialization also. So where multi-grid initialization, that will help to get the more accurate initialization at the starting level so that we can reduce our more computational time. Then we'll run it. So where we'll provide, so if you want to create some animation, we can create animation also. In this case, we have not create because it was taking more time. So then run calculation. Now we can give the number of iteration and we can calculate. For this case, I think this is part showing. So I'll show you this. After running, I have what plots. Plot. Okay. As of now, we have changed. I will open another case which we have done. Okay, in this case, let me close this and open the another one. I will take question in the meantime if you have any question. It has been messed. I created a model and it has been meshed when I trying to get. pivot warning error and counted. This is losing. Yes. So this is generally when you're putting wrong boundary condition, you'll get this kind of error. Okay. Now I will check in this. So the monitors, report plots. This is coefficient of lift. Now you can find out this is my coefficient of lift graph. Okay, and you can take out the average. So once you create the report definition, you'll get the graph like this. Even if you want to calculate, we can calculate also. Okay, so this is our coefficient of drag. You can see the CD. CD stands for coefficient of drag. Same way coefficient of lift. So whenever you are looking for the results, you can recheck them also. So generally student face issues, sir, I have run the simulation, I stopped, but I missed the plot part. How I can take that? So they don't have to run it again. They can simply see the report plots and there you can check the parameters values. Also, there's another, if you want to see in the console window, there's option to check also. Like if you go in the report definition, coefficient of car, and there's option compute. So it will compute total coefficient of car. Okay, but this is not the right way. So we go with the reports, fluxes, sorry, forces. So you can select all parts, don't type all. So I'll uncheck the ground, LED, and tunnel walls. So it will give you the forces on all parts. So this kind of pressure value you can add to your report. So it will enhance your report value also. So mostly students just they are giving simple value CD and CL. If you give the value like this forces report. So this is in X. X is equal to 1 means this is drag value. Okay. Same way if you change the origin to Y1 next to 0, you will get the forces of lift. Okay. Like this you can get the value. Now we have run this part. Then there is option surface. So generally we go with the contour first. Contour 1. So I will see the pressure contour. I given the limit. So there are two options here. One is the global range and another is the auto range. Global means I want to see complete throughout the domain. Okay. So it will compare the results with respect to maximum value throughout the domain. So if you see here, now this is our car. Okay. Here at this location, stagnant condition is there where we are getting the maximum pressure, and at this location we are getting the low pressure region. So means the velocity will be very high, suddenly flow. And on the upper region we are getting the maximum pressure, and you can see how much pressure is acting on the helmet. So you can see the design, and you can vary the design of helmet also, and you can see how the pressure value are reducing or whether it is increasing. Okay, same way you can check the plot of velocity also. So here we'll go with the auto range at this particular plane. Now you can see where we have the maximum pressure, we have the low velocity, where we have the low pressure, we have the maximum velocity. So this way you can check this parameter also and fundamentals of. Now if you want to see the car also here, what you can do, you can simply display, close, save and display. Now with respect to car, it will display. Velocity. So generally we have given color to this part, so it is not that much visible. Okay, but if you see here, you can display, draw mesh. Here also we have option, I can make it transparent also. 80 parents display. Like this, now you can get better visualization how actually the is there. Same way you can check for the pressure also. Okay. So this way, and we can create some ISO surface also, like particular to values where I want to know the parameters. So this kind of contour plots are very important, and you can visualize how actually view are going on. Okay. Now, if you see, I have created one ISO surface. So how you can create the ISO surface? Z is equal to new ISO surface. Okay. Here you can select the location whatever you want to create, or if you want to create some plane also, new plane. So directly it will show in the axis. So now you can change the method, and wherever you want to create, you can create also, and you can move with cursor also. Like this, we can create plane at any location, and you can measure the value at particular location. So when we have some internal flow, we generally check the pressure value at different locations. So you can cut the plane, you can check with that part also. Now here I have created the ZX plane with the surface of mesh Z coordinate and given the value of 6 ISO 6. Now I will check the vector at this particular location, and I increase the scale value to 3. Draw mesh. So like this, you can see the vector. If you hide this draw mesh vector also, you will get better visualization. We have option also, we can visualize the part, we can move the surface. Okay, and we can create the path line also. Path line will take actually more time to display, so I have kept in the slide. Okay, so this kind of results you can visualize. So generally what we have done in the setup, we have selected the turbulence model, we have applied the boundary condition. So boundary condition, our uh, wheel condition were very important, where we have given the angular velocity as well as the rotational direction also. Then Selzone condition, based on the material report definition, we have selected the lift and drag, and mass flow rate also. If you want to measure, we can create the mass flow rate also. Velocity also we can measure. Then in post processing, we check for the forces, like we have observed for the lift and drag forces. Contour we can create for the velocity, pressure. Vector also we can create. Then path line, like this, how it will move, and we can visualize the flow also. Then there is option in report generation also, how we can generate the report. So in the tool, we have option, we can simply go to the last part, simulation report, and report outline you can go, and you can generate the report. It will generate the report in PDF format or PowerPoint format if you want to create. So before that, you have to create the contours in proper way, set view, then only it will be beneficial. Just like Mayank sir have showcased you the parametric simulation, same if you want to do the parametric simulation with respect to your design, like you want to vary the velocity. So what you can do, you can go with the boundary condition. So you can put, so now if you see in this our workbench, I don't have any parametric setup. Okay. At this case, I don't have any parametric setup. So you want to, you can create there in CFD also. So go with the inlet, add it. Now I want to vary my speed, because in vehicle generally what we are doing, we are increasing our velocity. So I want to see at which velocity we are getting the max, how the drag value is changing. Okay. Just with respect to, I want to vary. So here you can go with the new option, new input parameter. Okay, 20 meter. So you can name it as parameter velocity inlet. Okay, now apply, close. Now since we are given the input, we have to create the output also. So output, how we can check, there is option report definition, and you can see there is option create output parameter. So you can create output parameter, and okay. So it will create output parameter. Further, you want to create further output, you can select any things like surface report. If you want to see the mass flow rate, how the mass flow rate is changing at the outlet if I'm increasing my speed. Then select the outlet condition here and get output parameter. So with respect to change in this part, any parameter you want to optimize, you can optimize, and then you can see in the workbench, this parameter will come. So you can see here parametric set. Now here I can change my velocity 40, 60. Then I can run it and I can visualize how the coefficient of drag values are increasing and how much it is increasing. Okay, so which speed is optimum for us to have the uh, drag value. Like this way you can check that part, and then later on you can optimize that part. So a lot of researcher have done published paper on this part also. So this is one case study. So they have optimized the design. So previously the design was like this, and they have seen the recirculation region, how it is, and they were able to. So you can go to Google also, you can find out this research paper, and you can see how post processing they have done, and for the vehicles, how they were able to optimize the wake regions and other regions. So this is the previous papers. So if we go with the respect paper, one researcher have done for the large. That's why I mentioned LES, large eddy simulation. So he have a lot of time. So even when you're in third year, along with the you're practicing, if you want to publish some paper, you can go with the some publication of your design also. You can do the CFD simulation and it will help you give more add-on value. So now comes the last part from where you can learn this program. So for this we have Ansys innovation course where students can take the fundamental concept learning, what is CFD, how we apply the physics, all those parts. Then once you learn the parts, if you are have your college institute already have the tools, and professor have the Ansys learning hub portal where we have the solved cases, examples, and advanced problem. There we have Ansys learning hub. So sometimes you get lot of queries. For that we have the Ansys learning forum, and if you want to get certified in these courses, you can get the certification also. So as of now in AIC courses, we have courses for all physics, fluid structure, electronics. Even you want to learn some Python related to CFD or mechanical, you can learn that also, and you can apply to your code also. And related to metal also, there is a lot of information. So more than 374 plus courses are there, which you can learn physics and engineering courses. Then we have ALH, where we have learning courses material for the research scholars and the faculties. This is not for the students, but if the college have, you can take help from your faculties also. Then this is forum where you can put your question and you can discuss with the, you can see already people have worked on that problem statement, how they have given the solution. Then you can get the certification. If you just like Google Play Store, we have purchase store also. Ansys, you can go to AC course. If you have completed the course, you can get the certificate like this. So these are few examples, and these are the batches. This is complete course certification. So these are paid and the learning is free of cost. And nowadays people are using ChatGPT. Same way Ansys have virtual assistant. So for students we have virtual assistant. For industries we have Ansys GPT. So you can ask directly question there if you get stuck somewhere. So it will give you the related material, content of material, which model is there, where. So you can search that type also. So I'll show you one course just like we have done. I showcase you this. So you can simply go to Google. You can type Ansys innovation courses. The first link you will see Ansys will come, and directly you can search here free courses. So we have physics also, fluid structure, electronics. So you can filter out the physics also if you're looking for any part. And if you want to search, I can simply type SE, done. You can download the student software and just for basic learning in your personal system, not in the college, in your personal laptop, to learn the physics in your free time. So there are a lot of courses, theory courses also there from NPTEL, from simulation point of oriented also courses there. So this is, you can see chassis analysis, BAJA SAE, chassis analysis related to FEA part. Okay. So if you want to see the aerodynamic, you can simply type the aerodynamic also in front, aerodynamic. Then it will show related to CFD part. So you can see this course here. You can go to this course, you can enroll. Learning is free of cost. You don't have to see, you can learn in this course how to create the model, front impact, side impact, all those kind of simulation. Okay, so I'm just pasting this link for your reference. Then we have, like I've searched, aerodynamic. So this, the example I showcase you, it's already there on the part. So you can go through these courses and you can see how they created the model. Okay, so it is around 4 to 6 hours. But if you know the fundamentals, you can go. So this is the older version. If you want to go with the latest version using Ansys Discovery, can go with the FEC. But for Ansys Discovery, we require good graphic card. So you might not have that much system laptop. So you can go with this course. Okay. But if you have good graphic card in your laptop, you can go with the advanced course also. Now we'll take question answer. So this is with respect to part. So they have the theory and the whole aspect. You can go to these courses and learn the basic part. Even if you want to know, like if you're new to the tools, directly you can go to the YouTube and you can search the Ansys learning videos. So Ansys have the channels which you can explore and you can learn the basic fundamentals of meshing and modeling part. So now we'll go with the question. How to define the coordinate of XYZ in relating the center of pressure of car. So you don't have to provide center of pressure. What do you mean? To define the rotation, you can go with the space claim. You can create the origin there and you can use the measure tools to measure the origin point. Okay, so in this case, they have created the origin. You can see in this video also, like geometry preparation. If you want to create in the fluent for the post-processing part, you have to create the ISO surface. There you have to see first to the contour where you're getting the value, then you can use the ISO surface. For particular value you want to see, you can give that value and you can see the graph. So even you post-processing also you can see here. So these are the videos already available on the YouTube. And for my case, in us, it is not enabled. So you can see at your end. I shared you the link. Okay, just check at your end using these links. Any other question? If you any other question, please let me know. Yes, we can get from space claim. So do
Rohit sir, can we wrap up this session?
yes, sir. I think we can wrap up now. And the
Okay.
student can reach out to me on this my mail ID for any further queries.
Okay. So thank you, Mayank sir and Rohit sir, for this wonderful session. So thank you, students, for joining.